We're ready to start. Good morning, good afternoon, good evening to everyone here. We have, as usual, a global audience, and this is great. My name is Isabel Milan. I'm from WIDIA Marketing. And today we are presenting the second part of the Turning Application course that we started yesterday with our presenter, Vladimir, who is our regional product manager in WIDIA. And this is just one of the many master classes that we are offering every week. So every week we have a different course. I really suggest to write us an email if you are missing any of the courses we offer. Next week we have hole making. And that's going to be another very interesting course. So today, as yesterday, we are going to do around 40 minutes presentation with Vladimir and then answering your questions. So please write your questions in the control panel on the right whenever you have them during the webinar and also at the end of the webinar. And Vladimir also added some handouts, some of our catalogs that you can download, and they can be useful to learn more about our products. And by the way, let us know in the questions if you want a third course with Vladimir on the WIDIA product portfolio, turning product portfolio. So I will leave you to Vladimir, and as usual, you will receive in the next days an email with a recording of the webinar, so you can share it with your colleagues, with your customers, or you can listen to it again. And as usual, feel free to share the invitation to our next webinars and also the recording to anyone who can find it useful. So Vladimir, are you ready to start?
I think so, Isabel.
Great.
Hello. Let's continue talking about the same topic we talked yesterday. So it is turning, it is a general turning, and it is more basics or...
Vladimir, sorry, we do not see your presentation.
Yeah, it will be soon. So at first, also, I wanted to point out what we talked yesterday. So yesterday, we talked about turning definitions. What is turning itself? I hope now presentation is visible. Please also let me in the chat if anything wrong. I hope also you can hear me. If somebody, I mean, if your neighbor maybe cannot hear, please check our settings and also maybe turn off, turn on the headset and headphones. Also, we passed cutting angles of turning cutter. So main cutting angles of the cutter and also main cutting angles of inserts, of cutting inserts. We also touched a little bit about cutting forces and power. Cutting data and recommendations about cutting data, and also talked about productivity and surface finish we can achieve after the turning application. Today, we will talk about three more additions to this topic. Basically, we will talk about cutting tool materials, workpiece materials, and also geometries, chip breaking geometries, so more applicable from WIDIA assortment. So a little bit, there will be a connection with our assortment too. But if you will want to go deeper into our turning assortment, we will organize a separated turning portfolio webinar when we'll talk about anti-vibration bars, particle grooving tools, and how to apply them, how to choose the best variant for you, and so on. And also we'll talk about catalogs a little bit deeper, where to find appropriate solutions. And in the end, we will talk about how to find, how to fight with wear. So some troubleshooting part. But at first, before I start, I wanted to touch some topics which were probably not clear enough yesterday. And also here, for example, on this slide, I made a mistake yesterday. Please, I'm sorry, I will need to correct myself when we talk about approach angle and lead angles. What is, one second, I will try to write something on the screen now. So basically there are two angles and they are situated in the same triangle. So in the same surface, if I can put it so. So here it's the angle of inclination of cutting edge. Here the surface, the line which is parallel to the axis, and here is approach angle. And lead angle, basically it's angle between the same line, I mean between the line of the cutting edge and a line which is vertical, I mean perpendicular to the axis. So basically, if I try to write it here, here is approach angle, here is a lead angle. This is a 90 degree. One second. So here, sorry, is approach angle, and here it's a lead angle. And basically, approach angle equals 90 degrees minus lead angle. So in different catalogs, in metrics and in inch, these values are shown sometimes. For example, in milling cutter catalogs, you can find that milling cutters for 90 degree or 0 degree machining. So basically, it's approach angle and lead angle. In Europe, we use 90 degrees abbreviation. And in inch world, we are using 0 degrees. So power, also some of you asked about cutting power generated. I showed a very simple formula. Also, there is a little bit more complicated one. Basically, it's power. It can be calculated like multiplying depth of cut on feed per revolution, cutting speed, and also multiplied by Kc. Kc, it's a specific cutting force measured in megapascals or in Newton per millimeter, per square millimeter. And basically each material have its specific cutting force. I mean, it's like a machinability. So greater specific cutting force, worse machinability usually, and higher hardness. And also coefficient of effectiveness of the machine tool. So usually here in this formula, it can be from 0.7 to 0.9, depending on the spindle quality of the and so on. So basically, if you in databases of materials, if you find Kc value and you know your cutting data, you can calculate the cutting power according to another formula showed here below. And pressure. Also, some of you asked about coolant. Sorry, coolant, yeah, can be used different depending on what material you are machining: aluminium, stainless steel, what type of wear you are faced with, and usually coolant should be delivered to the cutting zone. So directly, also, if it's directed with a high pressure, if it's delivered with high pressure, for example, 100 bars or 300 bars. It changes the cutting process. It's help chips to be broken, so and to make this machining easier and the tool life longer. Here, for example, you can see on the slides, you can the chip is becoming thinner because it started to break earlier. And here you can see how the coolant and a precise direction of coolant and also the high pressure of coolant help the cutting process in turning operations. For example, you can take from us the holders with a high pressure coolant. Basically, they are on KM clamping, the modular clamping. And here's a difference from one of the test results. For example, the same insert on the same cutter was tested on stainless steel. And here the comparison of tool life. So it's about 2 times greater tool life, longer tool life we achieved when we used coolant in smart way. So it's a short additions from previous webinar about your questions about coolant. And here, for example, how it can be delivered at very short video. Yeah, it's just a coolant. It's not cutting process anyway. But closer to the cutting edge, better results you will achieve during the application. So next topic is cutting tool materials. Before that, I wanted just to ask you if you were participating our webinars about cemented carbide inserts production and coatings or not. Just to want to learn if I should talk about it deeper, or I should talk about it faster, or maybe didn't talk. I should not talk about the cemented carbide now at all. So just you will see now a poll. Did you participate? It was this webinar was last week. And depending on your votes now, I will decide if I should talk about it. I think yes now. So about half participated, half not. Yeah, even more not. Yeah, thank you. So let's talk about it. Let's take a little bit more time about it, about cemented carbide. Not production, yes, I hope we will continue this webinar. Also, we will make the same webinars in future, just to remind about it. It's like a repetition, but here shortly we will talk about it now, about generally about carbides. So what is a carbide and why it's called cemented? Usually it's a combination of 2 elements, hard element and soft element, which stick together, hard particles. Hard particles, they are carbides. They can be different, but in most of cases it's wolfram carbide, WC, or tungsten carbide, it's also called. Also, these elements, both of them, but mainly the first element, has very high temperature resistance, and that's why it was chosen. Because during the cutting, the temperature can be 1000 degrees or 600 degrees in cutting zone. So cutting tool should resist to high temperatures and to not be destroyed or worn out very fast. So cutting particles, they are wolfram carbide particles. Also, they can be in others, for example, titanium carbide or another carbides, but in most of cases, we use wolfram carbides. Binder also can be different. Usually it's a metal. So WC, it's like a ceramic. Cobalt, it's like a metal. So in short words, it is a metal ceramics. Ceramic particles in a binder, in the metal binder. But binder should be also have a high heat resistance because it also participates the cutting process. And we can choose cobalt, also another nickelum, for example, or ferrum. But in most of cases, we use cobalt because also very important that it should have a good affinity, good reactivity to wolfram carbide during the production process and in application also. So the best affinity to tungsten carbide is a cobalt. So basically, this is a combination. It's pressed, sintered, and then coated. And the structure you can see in the right bottom corner. We can change the structure of the substrates or what we have inside the insert. When we are producing it, we can decrease or increase grain size. We can increase or decrease cobalt content, the soft part of the carbide, and also if we increase cobalt, we increase toughness and the heat and the interrupted cut resistance. And if we decrease cobalt content, we increase the hardness or wear resistance, and also possibility to work with higher cutting speeds, with high temperatures. And also with the grain size, we can do the same. Smaller grain size, higher hardness. Greater grain sizes, higher toughness. We can manipulate, we can play with it, and we can make different types of substrates. Also, why it's called cemented. Basically, it's hard particles cemented or stick together by cobalt. So there can be different substrate, one carbide or double or triple carbides. Additional carbides, they were added in the 30s years of previous century to WIDIA grades, and after that to other grades of the other companies. And the purpose of them is to achieve better chemical and thermal resistance to steel when we machine steel, especially in turning, because with the bigger heat, steel, which is a combination of ferrum and also with carbon, is reacting with wolfram carbide. So in order to resist to that, we add additions like a tantalum or tantalum niobium carbides and also titanium carbides. And basically the substrate or the tool material that time, because coating was not invented that time, it increased chemical and thermal resistance to the steel, and made possible to achieve higher cutting speed, higher productivity. But now most of the tools are used with coating, and coating was developed in 60s. Also, first patented coating by WIDIA in 1962. And in 1968-69, first inserts started to be produced. There were several methods. First of them, it's CVD, chemical vapor deposition. Usually it's a thick coating. It's a multi-layered usually. Layers can be different, but usually they're used as a sandwich. I mean, they add each other because only one layer. In the past, I mean, in 70s, probably used not probably exactly used one layer, carbon of titanium or carbon nitride of titanium. Also, it's not chemically stable at high temperatures, and we need to use another layers. For example, aluminum oxide, because this aluminum oxide, it's like a ceramic. It's very inert to steel, chemically inert, and also it not let a high temperature to go in to go inside that easy. So basically, it's these two layers are the main ones, and also they also are given higher hardness. For example, hardness of titanium carbon nitride is about 3,200 Vickers, and the hardness of uncoated grade is about 1,500 Vickers. So about 2 times higher hardness means better, much better abrasive wear resistance. And this allowed tools to work with even higher cutting speeds. Thickness can be different from 5 to 20 micrometers for roughing operations, 5 micrometers or 7. For high speed or finishing operations, it can be 20 micrometers. Also because of the very good adhesion due to very high deposition temperature, 1000 degrees during the production of the coating. At this temperature and more modern coatings, they used 850 degrees. Anyway, it's very high. and this layer, carbon nitride of titanium, deposit with such a temperature and have a good adhesion to the substrate. That's why we can achieve in the end very high thickness, very big thickness of the coating. And basically it's used for turning operations. Another type of coating, it's a physical vapor deposition. Layers can be also different, can be multi-layered, monolayered, gradient layered. Usually it's a process like a ion bombardment. It's not chemical reaction like in previous in previous type of the coating. And due to relatively low temperatures of deposition, adhesion is slightly low. That's why we can get only coatings with thickness from 2 to maximum 8 micrometers. Also, with the development of PVD coatings, we will be able to do thicker ones. For example, because it's not only ion bombardment, but also another process, it's called magnetron sputtering. And it gives to us a possibility to generate newer layers, unique layers, and also to help us with adhesion somehow. And in future, we will develop these coatings and it will be possible to make them thicker. Usually, this coating is being used on milling products, milling inserts, and also on solid carbide drills and solid carbide end mills. For turning also, we are using that for example, super alloys turning or for super finishing turning when we need very sharp cutting edge. So it can be achieved by PVD coating, not CVD. Also, because the coating is very strong, I mean, it has compressed stresses inside. That's why it's very reliable. I mean, PVD coating. And also, it's so thin, we can get very sharp edges because we can put also smaller, we can get a smaller edge radius because of the thickness of the coating. It's one of the way to how to fight with one of the types of wear like a built-up edge. So when some materials is welded on the cutting edge, for example, in stainless steel turning, and sharper cutting edge is helping to fight with that wear. So combination of substrate, one carbide, multi-carbide, and coating, PVD or CVD, let us to construct very deep portfolio of carbides, of cemented carbide grades. For steel, for example, and for stainless steel, they show their WP for steel, WM for stainless steel, and they're different for sure. Substrate are different because of the cobalt content, also because of the grain size, and also because of the thickness of the coating. So higher grade positioned here on this slide, thicker coating. If a grade is positioned more to the right, it has more cobalt inside, cobalt content. So it's very shortly about cemented carbides. Also, for sure, we have another turning grades like super hard grades, cubic boron nitride, ceramics, polycrystalline diamond, and also we can make a diamond coating. But let's go closer to the geometry. Not only grades influence on the productivity and efficiency of the turning process. Also, it's a cutting edge. Here you can see the cross section. There can be two cross sections. 1 second. Yeah. Here we show the cross section which is going through the radius. It's perpendicular to the cutting edge line here, but edge line here it's a radius. Also, we can look at the cross section of the main cutting edge. Also, it's very important because in the cutting process, they both are in the cutting process. And the edges usually different. But in general, cutting edge is consisted of clearance phase. We talked about it yesterday. Rake phase. Here is a chip breaker profile. And in the end of the chip breaker profile, we see so-called T-land. T-land is just like a line which can be positive, which can be negative, and which can be neutral. And depending on what we can get, this increased strength of the cutting edge to the hits, to interrupted cut, or sharper behavior. So we making this T-land positive or negative or neutral. Also, in the end, it's not visible, but it's a honing or edge radius. Not nose radius, but edge radius between rake surface and clearance surface. Depending on the size of the insert and depending on the grade too, frankly speaking, we have different edge radiuses. So bigger for heavy duty inserts and smaller for general turning inserts, or even smaller honing for finishing chip breakers. Also, depending on the grade, is PVD coating with a tough grade, honing can be done smaller with the same toughness because edge is reliable enough. With a CVD thick coatings for high-speed turning operations, usually honing is being increased also, not only because of CVD, but because of the higher hardness of the grade. Chip breaker profile. Because of this, we can get different types of chip. So the different types of chips can be get because of the cutting data and because of this profile. Usually we have a segment, we should have segment type of chips. And also we can get longer one, so which is not, which if it's not break enough, fast enough, we will get a problems when this chip will be in contact with cutting edge too many times. It will be rotated with a component or workpiece, and also surface finish will be not optimal. And here you can see one of the recommendations we talked yesterday. So basically, feed per tooth should be greater than the T-land. If T-land is neutral or negative, in order to be in order to let the process of chip breaking, the chips going into chip breaking profile in correct way. Not like here, this T-land is resist to chip to go inside, and it's not. It doesn't have any affinity to be broken. Depending on for the same chip breaker, we can get a different chip style and length and thickness also, because it also depends on the cutting data, on the depth of cut, and also on the feed per revolution. Because the depth of cut and feed per revolution gives us chip section, and chips. If a chip is too thin, you put very small depth of cut. You use for very small depth of cut, or for various you use very small feed, very small. So thin chip, it's hard for chip to be broken. So if you face with that problem, with bad chip control, you should increase depth of cut or end feed per revolution. And any chip breaker, every chip breaker has its application area. So it's a range of feed and range of depth of cut. If you apply inserts out of this range, there is a big probability that you will get chip unbroken. And if you put both parameters on maximum, maybe chip will be maybe even okay, but chip but cutting edge will be overloaded, and you will get a broken insert in the end if you will work in this area out of the application area too. And you can see here also on the same slide, there are two cross sections we are given in our catalogs. For example, our main catalog is with most of the technical parameters, the master catalog, and for each chip breaking geometry, we are giving to you two cross section pictures. One of them corner radius, it's going through the corner or through the nose, through the radius, and one of them on main cutting edge, it's here. Sometimes it can be different. Here it's more or less the same, only here you can see rake angles bigger, yes, in order to compensate, to make it a little bit working softer. But very often chip breaking geometries make it because it's for heavy roughing operations, this chip breaker. But very often chip breakers for semi-finishing, for example, operations for semi-roughing, in the nodes they are sharper. The tail end usually here is smaller or neutral, for example, but on the main cutting edge, tail end is bigger, a little bit, not 2 times, it's maybe 20%. And it can be negative. Why? Because usually on the component, when you cut the component in the beginning, on the surface, you can have some types of inclusions, or interrupted cut can be there. But usually the first recommendation is go by corner, by the radius inside the metal without interruptions. I mean, if there is no any interruptions inside. And this area should be more reliable, more stronger. So that's why usually it's it has a greater tail end there. So taking from the catalog this tail end, you can check if your feed corresponding to this value, I mean greater than tail end or not. So chip breakers usually they are different. For steel machining, for stainless steel machining, we have at least 3 of them. One of them for finishing, one of them for semi-finishing, one of them for roughing. Roughing is stronger with smaller rake angles, and for finishing, usually this chip breaker is sharper with a very positive tail end or without tail end at all. And the last one is designed for lower depth of cut and for lower feed per revolution. And one of them usually in the middle, so-called universal chip breaker. Here on these videos, you can see how these operations differ. Roughing operation and finishing, basically because of the depth of cut and because of the feed rate. Also, for sure, the first choice could be not in that such an ideal situation with the skin. Cutting process itself, if we look deeper, if we look with magnification on that, for example, on this example of sliding, it's like a direct turning process. It's based on the deformation of the chip of the metal when it's in contact with the cutting edge. So here is a rake surface, it's a clearance surface. Here is a area of chip of the deformation. So we can play with that using the different cutting data usually. So feed, depth of cut, and also speed, because usually if you apply normal cutting data, so this contact of the chip usually is going out, and before it going out, it's in contact with the rake surface, And depending on the material, we'll talk about material a little bit later, it can very long contact or very short contact or middle contact. Very high temperature is being generated there, not only on cutting edge, but on the rake edge also. And by using different tools and different angles and different cutting data, we can play with that. In a simple way, you can see this deformation, this short animation, how chip is going out. So if to compare how rake angle influence on that, usually if we have positive greater gamma angle, I mean rake angle, tool have a less cutting stress, but also it has shear stress which is not positive, which not good for cemented carbide. Cemented carbide is slightly brittle material. That's why we have edge around also operations of the edge. We need to stabilize the corner because it's brittle. And usually carbide afraid of any residual stresses or bending stresses, but they like compressed stresses, like cast irons also. You can compare it with these materials. And with negative inserts, usually carbide feel itself better than in positive inserts. And if to talk only about geometry, you can see, but generally cutting process of positive inserts for sure, it's much better, easy to cut if conditions are stable. You can compare the cutting behavior when we use negative chip breaking geometry and positive chip breaking geometry. So much more temperature is being generated in the variant 2 on the right, and slightly smaller amount of temperature is being generated in the left variant. So we came up to the cutting materials. Generally, we need to organize maybe separated webinar about cutting materials. Usually, they are divided by ISO, by type of materials, so and by color also. It's a P, M, K, N, S, H, and O. First 6 they are included in the ISO, and O is just additional group for composite materials. Why they are divided? They are divided usually because of their machinability and the chip type of chip they have been which is generated during the cutting process. So more or less it's the same for the one group. If we will talk deeper for steel, for example, operations, steel can be different. Low carbon steel, higher carbon steel, alloyed steel, tool steels with higher carbon content and with a higher hardness usually. In the middle is a P4, for example, group. So depending on these subgroups, P0, P1, P2, P3, cutting data and a little bit chip can be different inside. But in general, machinability is more or less the same. Also, we talked yesterday very little bit about specific cutting force. Here you can see the range about from 1,400 to 3,000 Newton per millimeters per square millimeter, so or megapascals. You can put it in that formula and calculate cutting power if it's needed. And usually we have some difficulties during the machining, even steel. Steel can be softer. For example, low carbon steels we can face with worse chip breaking control. They can have a thermal treatment. They can have different hardness, and they can have a different surface conditions. Can be skin. Surface can be very, very uneven. And that's why in the catalog we put different cutting data for each of these different cutting speed, first of all. depending on the conditions, we are using different carbide grades. Harder grades, WP15 CT, WP35 CT, it's softer, the softest grade for the turning of the steel. And in the middle, the universal grade, WP25 for semi-finishing, semi-roughing operations. Also chip breakers, depending on the conditions, if it's interrupted cut or we need to achieve bigger, greater feed per revolution, we are using RH. RH is the first choice when there is no any other limitations like surface finish, for example. We just need to cut off maximum stock per minute. We use RH with every grade shown on the previous slide. But if we need a good surface finish, the stock need to remove this very small, depth of cut very small, we use ML like a first choice, or FF. Also, yeah, it's not short FF. Each of these chip breaker has its application area. I showed this in the past. And also this application area differ from the size, because it can be CNMG insert, it can be CNMG 12, CNMG 16, CNMG 95, or 25, sorry. And maximum AP also will depend on the size on the insert. If to talk about only one size, respectively, you can compare cutting data for them. You can see the maximum feed depth of cut can be implemented on RH chip breaker, and the minimum ones for better surface finish we can use on FF. Also, the charts can be you can find in our catalogs. Also, logically, we can take optimal combinations for different roughness and also for different conditions, stable condition or unstable conditions. For example, if a condition is slightly stable, I mean, but even if you want to apply very high feed, you can use the hardest grade, WP15 with RH. On stable, it will get a maximum tool life, even if depth of cut is big, if it's 7 millimeters, for example. But if it's not even surface, it's flats or slots and so on, or skin, for sure we need to use a softer grade with less cobalt content and thinner coating. With stainless steel, also we have some challenges, because usually there is a big variation of cutting forces. I mean, in average cutting forces may be more or less the same, but it's changing. It's changing a lot. It can be minimum, then maximum, then again minimum, then maximum, and that's why our cutting edge is overloaded, and machinability usually up to 2 times or more worse than the machinability of steels. And you can see the specific cutting force is, yeah, it's not that higher, but also because of the surface of it's usually slightly soft material, and also it's harder to cut. Also, it's chip. If you look at the chip, which is going on the rack face during the cut of cutting of the stainless steel. 1 second. So here. So chip contact length is much higher, much longer than in comparison with steel turning. In comparison with cast iron, maybe chip starting to be evacuated here. In steel, here in stainless steel, it's the longest contact with the rack face and with the cutting edge itself. And we also apply different grades for stainless steel. For interrupted cut, WM35, WM15 for stable conditions, and for semi-finishing, WM25. Also, the separated line of chip breakers. Also, it has a range of depth of cuts and also feeds per revolution. Cast iron, not that hard to cut materials, but also it has some challenges. Usually it's not that high quality materials, and also it's cast. It can have a lot of inclusions, and also it have a higher hardness, high toughness, but usually it's a brittle material, and the chip is very brittle. It's like a dust. So usually it's easy to cut such kind of materials. We can use different types of grade there, but usually they are very, very hard. They are harder than grades for steel. For example, WKO5 and WK15, they are harder than WP15 CT grade. We have different chip breakers, for example, CNMA, because we don't need any additional chip breaking control during the cast iron turning. But if we need higher toughness, we can use RH in addition. If you need this chip control, because some cast irons, they can have some inclusions. For example, in oil and gas industry, we are using, not we, but customers are using cast iron with alloying by nickel and chromium. So they can have a chip like a chip from steel. For that reason, we can use UR or ML chip breakers. Also, we can face with the chipping of the corners of the component during the turning of the cast iron. If this problem appears, we are using sharper cutting edges, usually ML or UR with the WK grades. So here you can see how chip looking like when turning off the cast iron. It's a short segment chip, and it's almost without any additional contact on the rake area. If the cut is very interrupted, we can use grades for steel, for cast iron. So the last topic for today, it's how to fight with wear. So how to so-called troubleshooting session. Usually, if we are you are not seeing the process itself, you just hear some rumors. So rumors can be different when there are problems with the cutting edge. Some can say to you, insert is burning. I mean, how to analyze that without looking what is happening? Just hearing this word, it's not possible to understand how to fight with this with the problem. So basically, these words are not saying to us, I mean, to cutting tool producers, it says nothing. What is the burn? Burning is not wear, it's not a type of wear. Insert is crunching. Inserts are not staying. Inserts are not working. Size is going out. In order to get the truth, we need to come up closer. What is going on in the cutting process? How to understand that something is wrong? I mean, that the wear appears. For sure, we cannot measure wear every minute. Usually, there are some criteria, some parameters we can monitor and understand that something probably wrong with the tool life. First, it's a spindle load. You can look at the CNC, some of the machine tools in CNC are showing the spindle load or the power in percents, and it starts to be different from what it was earlier. Then probably cutting edge is deformed, cutting edge changed, and maybe wear appeared. Change of surface finish, roughness has been changed suddenly. Change dimensions of the component. In the end of the component, dimension is diameter is 1, in the beginning it's another, so probably the wear appeared. Change size of the chip. You can see that chip generation is another, so it was with short segments, and now it started with long segments. Probably cutting edges were not. Vibrations, so cutting forces increased. You can also, and also sound of the cutting is changed, so probably it is a wear. So what to do with wear? Depending on the type of the wear. So if it's flank wear, you can see here how it looks. On the flank, also on the clearance face, there is a line which is abrasively worn out. it's slightly even, and it is a maximum positive wear we can face with. We need to achieve this wear, but if this wear appears not very soon, usually it's abrasive because of contact with material for sure, because of the abrasive friction. It can be if it's too early, if it appears too early. It can be because of the too high cutting speed, or maybe grade is not hard enough. So basically, first, what we need to check when we face with such of wear, to check minute tool life. If it's a 15 minutes in cut, this is normal. For general turning applications. For heavy duty, it can be 30 minutes. But yes, if producer of metal cutting workshop wants more, you can try to change something. For example, reduce cutting speed, but we cannot compromise with the productivity. So basically, we can change the grade for the harder grade. At first, it should be done in the beginning for sure, but if something changed in the production process and the inserts are being used the same, we can help to change inserts for those and change grades to the grade which can be applied better for the changed conditions in the workshop. Increase feed rate, also sometimes it's happened, I mean, like a compensation. We can reduce cutting speed and increase feed rate instead of that. Get better coolant and pressure of coolant. So another wear is a chipping. So basically, why flank wear is the most is the best wear we can face with, because it's a stable. I will try to write down. Yeah, here it's a wear axis. Here's the axis of time, and usually flank wear it starting here. It's initial wear. It's maybe, I don't know, in a minute it's appearing. But after that, it's developing, growing, but not fast. It's a line in general. And then after 15 minutes with a higher cutting speed, it's a catastrophic wear. It's increased dramatically. And if we play in this period of time, everything is stable and we can foresee what will be next. I mean, if we measure here, is the way we 0.008, for example, but here it will increase, but not much. So it will be 0.01 maybe, no, 0.1, sorry. So depending on the application, heavy duty finishing, these criteria, these values, critical values can be different. And it's a very stable type of wear. If we face with chipping or with, for example, crater wear, it's not that stable. So it's just appear and then up and going up. And we don't have any time to play with it. So basically, we need to turn all types of wear to flank wear. For sure, with normal tool life. So if we face with chipping it's a brittle wear. It can appear because of vibrations. If the system, I mean machine tool, cutting tool, equipment which is clamping workpiece and or overhang is too big, there can be vibrations. Interrupted cut because of the component. Big variation of forces because of the material. Too brittle grade also, too sharp geometry. So how to fight with that? Check rigidity at first. If everything is okay, if nothing can be shortened, like overhand, for example, or clamped better, we need to try to use or stronger geometry. If it's a vibration from the component, component cannot be more even, for example. If there is a vibration due to component that is very thin, for example, and it vibrates because of that, it's very, very thin, we can choose sharper geometry, not, for example, UR, but EML, or maybe positive insert from negative CNMG to CCMT, for example. Or use tougher grade, more resistant to chipping, to brittle type of wear. For example, from WP15 go to WP25. Plastic deformation. It's looking like shot here. So it's like a melting, some sort of melting or smelting of cutting edge because of the high temperature in the cutting zone. Usually it means it's too soft grade for this application, or very bad coolant delivery. So it's not constant, for example, or not enough pressure. So at first we can reduce cutting speed, we can reduce feed rate in order to decrease temperature in the cutting zone. It's at least temporary we can do that. But for more reliable continuation of the process, we can check the coolant. We can also try to choose a harder grade if operation allows it. For example, stable cutting, we can use WP15 CT or even WK20 CT. Our cast iron grades are even harder than WP15, can be used for P05 application area. Or to use sometimes sharper geometry to decrease temperature which is generated during the cutting process. So next type of wear, notch wear. So what is notch wear? Generally, it's like a big wear on the end of the cutting depth of cut. Here is a round insert, for example, ceramic insert. But for example, if we look at our rhombic style, so here is a component. Here's the depth of cut. This is a feed. This wear appears somewhere here in the end of the cutting of the contact. So what to do? And it's much bigger than the wear here. Here maybe there will be no wear, or just, I don't know, 0.05. Just you can see the line, but it's not wear. Usually it can be because of different reasons. If you used uncoated grade on steel, it can be because of that. It's a chemical reaction. Because here's oxygen here. A lot of there is a enter to the oxygen here, not because it's inside the metal here. Yes. Also, it can be because of the self-hardening of the surface. Very often we face with that type of wear when we machine stainless steels or heat-resistant superalloys. So what's the self-hardening? We cut one pass, when we will cut another pass. I mean, after the first pass, this area is hardened. Hardness can be increased almost up to 2 times, depending on the material. And after that, you will cut with this tool next time, and this layer will be much harder, and it will worn out the cutting edge. So what to do? Use a stronger geometry. Choose coated grade if it wasn't coated. Use harder or tougher grade, depending on what it was, because it can be because of skin. Skin, yes, it's not stable thing, but it contain inclusions like also carbides, and harder grade, better cutting of skin or resistance to abrasion wear from skin. Or tougher grade, also because of the residual stresses are being generated here when it is self-hardening. So sometimes we need to try to tougher grade. One of the very interesting methods is to have a different depth of cut each pass. First pass, for example, 2 millimeters, next pass 1 millimeter. So every time the end of the contact will be in different area, or to use conical turning, so not straight, but I mean to go to the deep or go to outside. Pump cracks or thermal cracks can be occurred when it's the contact is or load is very interrupted or varying a lot. On stainless steel, sometimes it's happened on steel too. So usually we need to check coolant, because also it's a thermal crack, and we should increase thermal situation, should be constant, or higher heat should be there, or lower heat, but more or less constant. Choose tougher grade if it's not possible to avoid by coolant, or turn off the coolant also. Or we can choose PVD coating. Also, it's not possible every time to do the same. Reduce cutting speed if nothing to do, if we cannot do, if nothing helps. And one of the very interesting ways is choose newer grade. because in newer grade coatings, they are tougher, they are more ideal, so they have more ideal structure, and they resist to this varying of the load and the temperature much better than coatings on the older grades. For example, TN 7025 resist to such kind of wear much worse than WP25. Built-up edge, it's like a welding. We talked about it a little bit earlier. So usually we face it in stainless steel turning, and this means it's not enough temperature there of cutting. So that's why here it's a welding. We need to increase cutting speed to avoid, but much, not just 10 by 10 meters per minute, but maybe from 100 meters per minute to 180 minutes per minute to increase temperature a lot. And we will increase productivity, and we will avoid such a kind of the wear. Also, we can try to use more positive geometries, more polished geometries, use emulsion with better oil contact inside. And also we can use PVD coatings. They are usually inserts with that sharper and softer. Also, you can see some sort of built-up edge, but it was chipping in the beginning. It was a previous type of wear, and on the chipping on this not even surface, metal is welded. So if it's chipping, not look at this. Look at the remedy against chipping. Crater wear, it's not so easy to find such kind of wear today. Usually it's too abrasive workpiece material because contact is here, main contact during the chip evacuation, or especially if it's uncoated grade, or not positive chip breaking profile here. So basically we need to choose harder grade or reduce cutting speed or choose more positive geometry in order to chip not contact with flat type negative type, part of the chip breaker, but chip will go inside the chip breaker and go out. There will not be bigger resistance to friction between the workpiece material and the cutting tool material. And breakage, one of the main reasons for breakage is if we didn't look at the wear before. It was crater wear, it was a flank wear, it was complex, built-up edge, and we didn't look at that. And finally, we are getting breakage. But usually, there is some time should pass before that. If breakage is appearing immediately, that's something wrong. Usually, it means that maybe grade is too hard, too brittle. We need to take a softer grade or stronger geometry. Better to start with stronger geometry. We need also to check rigidity. Maybe it's because of vibrations. Also, it's possible to reduce cutting data. And also, yeah, basically, maybe it's too big load because of the cutting data, too big hardness, too big depth of cut and feed together, and we cannot change it maybe. So we need to change the tool size to greater size. I mean 1606, thicker insert, for example, a holder also, or to stronger insert shape if it's possible according to geometry of the workpiece, from CNMG or DNMG to SNMG or SNMM. Also, we have such a brilliant chart, what influence on what, on which type of problem of wear. But basically, main recommendation, usually if somebody complained on the breakage or insert was burnt, was broken and so on, it means first analysis should be earlier, not in the final stage. For example, tool life is 100 pieces or 15 minutes. Check it after 5 minutes. Check the cutting edge, and if you understand which wear was in the beginning, plastic deformation, cracks, so you will be successful. You will find the right way how to avoid it. And tool life should be usually for turning, general turning 15 minutes, for milling from 30 to 40 minutes. So different standards for different types of operations. So here, that's all. Sorry if I delayed again. Now I am ready for your questions. if you have time. And also in handouts, you can download, for example, the different documents. If you open handouts now, for example, one of them called application guide. If you open it, this PDF, or download it after, you will find some remedies there, how to avoid wear, depending on which type of wear. And also there is a chart of grades we are having for turning, and not only for turning, for all types of operations. Short tips and some help in choosing of the geometries also, depending on the feed, also showed there. Yeah, if you have now time, please ask questions.
Vladimir, I can ask you a few questions.
Yeah.
So how long does it take for PVD and CVD coating to be completed?
Depends. It's about from 8 hours to 15 hours, so something like that, depending on which thickness we need to achieve, basically.
Okay, and why is the T-land, isn't the T-land the same in nose and cutting edge?
Here, basically because it's RH geometry. I mean, I hope it connected with that slide when I showed RH geometry. Because this geometry is very, very strong, and it should be applicable in different type of heavy-duty applications. It means even by the corner, it should resist to the hits, to the interrupted cut. That's why T-land is the same on the radius and on the main cutting edge there. Only because of that. For semi-finishing applications or chip breakers, this value usually is different. Smaller on the radius and bigger, a little bit bigger, but sometimes not. So it also depends. I'm not a designer of the tools. I know something, yes, but better to ask who designed concretely this chip breaker. But basically, because of RH, it should resist on any type of hits, even on the corner. And 0.25 is not that much. I mean, for example, for super heavy duty geometry, SR for bigger inserts for 7 cm 25, this value is about, if I remember well, it's from 1. It's not even, yes, it's from 1 to 2.5 millimeters. So basically, it can be much greater, but for heavy duty.
Okay, and which is the best grade for long overhanging boring bars, Vladimir?
It depends on a material you want to machine, but usually if it's a steel, I would try to start with the first choice. If it's steel, the WP25CT, to choose geometry. I mean, medium sharp geometry. So for negative inserts, if it's hole slightly big, it's a UR or MR geometry. For smaller holes, for example, 30 millimeters or even smaller, positive inserts like a CCMT or TCMT. But to be sure that holder with these inserts leads to approach angle 90 degrees. But usually WP25 should be okay for the start. If tool life is not enough, you look on the wear type. It's a brittle wear type, I mean chipping, or abrasive wear type like flank wear. You can change this grade in the first to WP35, and the second, I mean when it's abrasive wear, to WP15. But usually the first choice is the same like for all turning inserts. If it's stainless steel, if it's you need to cut very thin stock, yeah, PVD grades can be first choice also. WS25, it's very good for long overhang. Yeah, sorry, forgot to take into account if it's long overhang. But usually, if it's long overhang, we need to do something with tool, not with grade first. What to do? to choose, for example, instead of steel material of bar to carbide. We also have it. If your overhang is bigger than 6 diameters, or sorry, then 4 diameters, from 4 to 6 diameters, the first choice is carbide holder. If you need to go even deeper, and we have assortment of anti-vibration bars from diameter 50 of hole for 10 diameters and for 15 diameters. The first choice is to choose something with the tool, to change something with the tool itself. The second, chip breaker. If it's long overhand, if there are vibrations, choose a sharper chip breaker, for example, ML. If there is no any big deviations of the profile of the, of the surface of the skin, if there is a skin at all. So if there are no any instability in the workpiece, just overhang, you need to choose sharper geometry and start with WP25. Then look if you need, if nothing happened, or you can choose WP15 and also calculate the tool life. Look at the tool life and try to choose the hardest grade. Maybe not at the first, but at the second step, optimization step, you can go to the hardest grade and get the maximum tool life, or to put higher, to adjust higher cutting speed.
Great, Vladimir. I think we can do the last question because we are a little over time, but we will try and answer. We can also answer more questions if you send us an email. You reply to the confirmation email of the webinar or the follow-up email and just ask us the questions and Vladimir will answer. So how does the
answer in the third part? If you would like to have a product part, we also will try in the beginning, like today, to answer some questions in the next webinar. Okay, what is the next question?
Yes, the next is, how does chip flow differ on nose and cutting edge?
Usually, yes, it's not the same. 1 second, I will try to go in very back. Direction it's not the same, because usually the chip control. 1 second. Yeah, if feed is 1 second, is in this direction. So basically, if chip breaker is more developed here than here, so basically chip is going on the right face, and here the most developed chip breaker, and the chip control is much better. Chip creation, segmentation is better. Here, yeah, it's not that good. So if you will cut only this part with a small depth of cut, chip will go, yeah, not directly, or some of type of part of chip will try to go there, and there is no any barrier, you can see, and also some will go there, and it will complex direction of the chip. So it can be not ideal here. That's what I can say now, and you can find the problems. So that's why for finishing chip breaker, this chip breaking profile is coming to the corner closer, in order to avoid such kind of situations. So in order to have this barrier, this perpendicular barrier to the chip, and more or less developed chip groove. Yeah, this is the answer. If I hope you got the point. If you have another questions or another wishes, please let us know.
Yeah, and they said that explanation was good, and I think we'll stop here for today, Vladimir. But since there is a lot of interest, I think that a third webinar on turning could be really good, and we will be sharing more information with you all. And for the people who have already registered, we will speak again next week. On Monday we have full making. And I thank you for being here today again with us and with Vladimir and Tony. Bye bye and have a great weekend.
Yeah, bye bye.